Hello, it's Keith here, and this is lesson 42 of the platform-specific series of my 68000 assembly programming tutorials. Today we're going to be looking at sound, and we're going to be looking at it on the Amiga. We're going to have a look at making a new sound driver. We made a little simple sound driver called ChibiSound before. That was designed for simple bleeps in a Space Invaders type game. This is designed for music, and it's called ChibiSound Pro because it's a little bit better than the original, although maybe doesn't deserve the Pro moniker, but it's a bit of a joke. Anyway, what this does is it takes a total of 3 values that are passed to the set routine, and this will configure the sound channels. The original ChibiSound could only handle a single channel and only use single byte parameters, which was very limited. This one, not so much. Now, the first parameter is in the D3 register. This bits 0 to 6 are the channel number, and bit 7 is noise on off. Now, if you wonder why we're using that odd format, this is because we're mimicking the registers that the Z80 version used. You see, this is designed to create a multi-platform music piece of software that is called Chibi Tracks. Now, this will play the same binary file on a Z80 system, a 65002 system, or 68000 system, and probably more going forwards, and also many platforms on those systems. So we're working in a compatible way. Now, as well as the channel number, we then specify volume. This is a single byte in D6 from 0 to 255, with 0 being the lowest volume and 255 being the loudest. We then have a 16-bit pitch in D2, and this is the pitch from 0, which is a low pitch, and to 65535, which is a high pitch. Now, on all of the systems, that will be consistent, but the value, for example, 32768, will not be the same note on every system. Now, the way we get around this is we have a lookup table of the notes in the octave, which will allow us to get matching notes on all the systems, and that will allow us to play music on all of our systems in a roughly similar way. Now, sound on the Amiga is basically using wave samples, so we have to provide a digital sound sample, and then we can change the pitch that this sound sample is played back. So that will allow us to make our music. We're going to basically provide just 2 simple waves. One is going to be basically a square wave, and one is going to be a distortion wave. Now, the Amiga has 4 sound channels, and these are split basically into 2 left channels and 2 right channels. So if we want a sound to be in the center, we would need to make both channels sound simultaneously with the same sound. Now, with regards to our software today, we're going to be roughly trying to mimic the AY sound chip on the Z80 systems. So we're going to need at least 3 sound channels. So what we're going to actually do is we're going to use those sound channels separately, and effectively we'll have 4 of them. Now, there are a couple of other things we need to know about. Now, the way that the digital sound works is we need to set a DMA up, which will automatically keep transferring new data to the sound hardware to keep the music playing. So we're going to need to operate the DMA control register. There is also an audio control register as well, which handles some of the special effects with regards to the way the channels affect each other. We're going to turn that off. Now, beyond that, we basically have a 16-byte sequence with a set of registers that are repeated for the 4 audio channels. Now, these aren't all used, and we won't need all of them, but basically these are used to set things like the memory address of the wave data, the length of the wave data, the pitch is called the period in this case, and the volume, and then there is a data byte, which I think you can read the data that's currently being played and things like that, but we don't need that. Now, we're going to need to set all of these up correctly for our waves to play. Now, one important thing that you do need to know about is that the location of the wave data must be in the chip RAM, that is in the sort of core memory of the system, as opposed to the upgrade memory. For the hardware to access it for the DMA, it's got to be in the built-in memory. Okay, so that's what we're going to be doing. So let's go over to our source code and let's hear some action. Let's turn on our oscilloscope here, and then we can see the waves. So the first one we're going to run is this ChibiSound Pro test. Now, this was used for testing the driver and the configuration. Basically, all it does is it creates a constant note. If we just get our emulator over here, we run it. Now, if I use the joystick, where is it here? You can hear we're able to change the pitch value directly, and this was used for testing. It was also used for building up the frequency table. Now, the other thing I can do is if I change the pitch to a nice high pitch, you can hear that I'm able to affect the noise option by pressing the fire button. Now, this was just used for the configuration and testing, as I say. What we really want to be able to do is we want to be able to play some music. So this is the example that I've got at this stage. I'm still finishing the software, just doing some sort of documentation, debugging of it and that kind of thing. But here it is running on this system. Now the music we've got here is the converted version of the Chibi Akamas theme, which was ported to the Amstrad CPC for the Chibi Track software for the 10K subs special. It was originally written in Arcastrack and then ported to my Chibi Tracker Pro. But the binary that exported is able to be played on all of these different systems without re-exporting. So it's the exact same binary that works on the Z80 and works on the 68000 systems on this Amiga. So it doesn't sound quite the same on every system because of the technical limitations and things, but as I say, the point is that we are able to play a file and we don't need to keep recomposing our music, and we don't need to worry about the exact capabilities of the systems. That is the plan anyway. So what we're going to do now is we're going to take a look at the driver that handles this system. So here we go. So this is the driver. Now the first thing you'll see here is the Chibi Octave here, which Octave is now spelt correctly. You might have noticed on the other 68000s. My terrible spelling got the better of me and I misspelled it, so I've corrected that now. So what we've got here is basically a lookup table of the 16-bit values for the various notes in the octave and the various octaves down here. So when we want to do a pure tone, we would just read in a single value. But if we wanted to do A sharp or A flat, we would basically take two values, add them together and divide by 2. So we would take G and A and add them together, divide by 2 to get A flat, or A sharp. We would add A and B there together and divide by 2. That's how we would calculate them. So that's very easy. Now at the start of our initialization, basically the first thing we're going to do is we're going to update this audio option, and as I say, this affects the ways that the various channels can alter the pitch and also the volume. I believe you've got some kind of envelope functionality. Now the way this works is a little bit odd. Basically the top bit, it's marked F there, is either 1 or 0, and that defines the rest of the bits as either enabling or disabling the functionality. So where a bit in the remaining bits is 0, no change is made, but where a bit 1 is set in the remaining bits, the change is applied. So these bits being 1 mean these bits are going to be changed, and because the top bit is 0, it means those bits are going to be disabled. And what we're doing is we're disabling that envelope functionality for all of the channels. If the F was 1, then this would be enabling them, and if those bottom bits were 0, it really wouldn't matter what that top bit was because no change would occur. We'll see that later with the DMA. So we're there just disabling that frequency modulation options there. Now what we've got here is this ChibiSound update option here, and this will be run every tick, and what this is doing is it's re-randomizing the noise wave sample. So we've got a simple random number generator here, or we can use another one if one is provided, and we're basically rewriting the bytes of the wave file. And that is something we do need to discuss at this point, I think, is that we need to actually provide some wave data. So we've got a simple square wave tone here. You can see it just goes up and down here. So that's a square wave. And then what we've got here is some random data here. And this isn't particularly random, but this will be constantly being rewritten by this random number generation routine here, which, as I say, this ChibiSound Pro update is run every tick that the music is updated. On a system like the ZX Spectrum, which is a beeper system, we actually need to use the processing power to keep playing the sound. On this system, we're simply just re-randomizing the random noise data there. So that's what we're doing in that case. Now, when we actually want to change the notes that are being played by the channels, we run this ChibiSound Pro set, and we've got our parameters here, the volume, the channel, and the pitch. And the pitch is 16-bit, the other two are 8-bit. So the first thing we're going to do here is we're actually going to turn off the sound DMA. Now this is so that nothing gets changed while we're messing with the values midway. We want to just stop it for a fraction of a second. So what we're going to do here is we're going to change all 4 channels, 0, 1, 2, and 3, and we're going to turn them off. So we've got the top bit set to 0 here, and that means that those will be turned off. Now at the very end, you'll see we've got another write to that same port at DFF096 here, which is the DMA control, and we've got the bottom 4 bits set to 1 again, but this time the top bit is set to 1, and that is turning them on. We've also got bit 9 set to 1 here, and that is enabling the DMAs. If we had that disabled, then it wouldn't matter what we did to 0, 1, 2, and 3, it wouldn't turn them on, but we don't need to turn that off. We're just turning the channels off directly there. So that's what we're doing there. Now what we're going to do next is we're going to need to decide what channel address we're going to be working on, because the base of the first channel is DFF0AO, the second channel is DFF0BO, and so on. So there's 16 bytes per channel, and we need to decide which channel we're going to work on. What we're doing here is we're just going to back up D6 into D4, and then we're taking the bottom 2 bits of D4, because D4 could be specifying a channel from 0 to 127 in theory, and so we've only got 4 channels to work with, so we're just going to wrap them around. What we're then doing is we're going to basically effectively multiply that value by 16 by shifting it 4 bits to the left. This is effectively calculating our offset, and then we're adding DFF-OAO to D4. So we've now calculated the offset for the channel that we've been asked to work on, so AO, BO, CO and so on, and we're going to move that into A2, and we're going to then write all of our settings as offsets from that, because we're going to have to set various settings, but they're always going to be an offset from the base channel address. Now we've now got our base channel address. The first thing we're going to do is we're going to set the pitch, which is in D2. But the pitches I'm passing, a low value is a low pitch and a high value is a high pitch. But with the Amiga, we need to specify basically the speed, I think it is, to update the sound sample. And so we actually need it to be the other way around. So we're flipping all the bits of D2 there, and then we're writing the 16-bit value from D2 into A2 offset by 6. And that is because A2 is now pointing to our base, and offset by 6 is the audio channel period, which is the frequency of the sound sample basically. So that is what we're doing there. Right, so we've set the pitch. What we're going to do next is we're going to set the volume. Now our volume is a full byte, but we actually only want 6 bits. So we're basically taking the top 6 bits, shifting right by 2 bits, and we're then writing that to the register offset by 8 here. And if you look here, we've got A0, A8 there, and that is the audio channel volume. And as I say, that only wants to take 6 bits. It's 0 to 64, with 64 being the highest. We're only going up to 63 with the way it works here, but that is almost full volume. So I think it's either almost exactly the same thing or literally the same thing. I'm not entirely sure about the way it phrased it. It wasn't quite clear whether 64 and 63 were the same or whether they weren't. Anyway, so we've now set our volume and we've set our pitch. The next thing we need to do is we need to set the kind of wave sample we're going to use. So are we going to make a noise, or are we going to make a tone? So what we're going to do here is we're going to load the details of our tone. We're calculating the length of the tone sample here. We're subtracting the end and the start and dividing by 2, so we've got that value in words in D0, and then we're loading the address of the tone into A0 here. What we're going to do next is we're going to test the top bit of D6. Now D6 is going to specify the channel number, but the top bit defines if the noise is on or off. Now if the noise is off, we're just going to skip the next bit and we're going to use those values, but if the noise is on, we're going to replace those values and we're going to specify the length of the noise sample, and we're going to specify the address of the noise sample. What we then do is we load in whatever our address of our sample and our length of our sample is into offset 0 and offset 4. Now offset 0 would be this one here, and that is the audio channel location. Now there's a high and low pair there, but we're basically writing those all in one go here. So that's what we're doing there. You notice we're writing a 32-bit long there into the offset 0. Offset 4 is the actual length of the sample, so that's what we're doing there, and it's got to be in words, which is why we were dividing the byte count by 2 there. That has now set all of the settings for the channel, and then the final thing we're doing here is we're turning the channels back on here. Now I suppose we could have actually just disabled the one channel we were setting, but for now I've got it just set up with this simple way of disabling all the channels and re-enabling all the channels, and it sounds okay. If I didn't disable the channels at the start, I was getting some quirks with regards to the sound samples, and I think it was because the sound samples were actually updating as I was changing the parameters of for example, the source address and things, and I think that was causing some trouble. So there we go. So that's how I'm setting the sound samples today. Now, if you've liked what you've seen today, please like and subscribe. But if you want to support this content, if you don't have it already, you can buy my book. It's called Learn Multi-Platform Assembly with Chibi, and there's 2 versions. The first one covers Z86, 502, 68000, 8086 and ARM, and then there's the new version which covers ARM Thumb, 6809, 65816, PDP-11 and RISC-V. So there are now 2 books, and so if you want, you can buy those from Amazon in print or digital. So anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.